P1, but the structure, the structure, totally different. I don't understand why. Just
Later, I just indicate that. Okay. Okay, morning, guys and girls. Today is the fourth and final class of this course. Last time, Professor Yongwei Dong talked about some applications dealing with the distribution of species around China in the world, some basic basal literature evidence, and he showed that there are strong implications about the responses at ecological and individual level of climate change affecting the distribution of organisms around the world. In the past my class, I just showed you different effects of climate change drivers on the ecological effects and ecological responses. And then that was the first part of that class. Now we just start again from where we left last time, just recalling two important models, two important information that are usually used by all possible organisms in this planet around the world, above all by ectotherms with an indeterminate growth. And then this is, I just for recalling it, this is the von Bertalanffy model showing that every organisms along the time has this growth model. Is a matter of energy. If you decrease the energy available along the lifespan, you have a decrease in terms of body size. And this is really important because we can, using the von Bertalanffy model and the energy budget modeling, we can actually predict which is the body size of organisms affected by changing conditions around. Main drivers are essentially two: food availability and temperature are the two main drivers affecting the growth of organisms. There are a lot of other drivers, but food availability and then the ability to access to the food, or just the amount of the food in the habitat and the thermal profile along the lifespan are the two main drivers. If these change, these two change are subjected to some changes, then we can have a reduction of body size along the lifespan. And then the first, under pristine conditions, is just what we call control reference conditions. In this case, we have the optimum, the ideal growth with the ideal reaching body size and the desired or the wished body size in theory for the theoretical and optimal organisms. But in the reality, in the real habitat, with reduction of body size, of the food availability due to different constraints in the habitat, competition by other organisms, we have an effect in terms of diminishing, reduction of body size, and this has a really strong implication. In theory, if you reduce the energy and the thermal profile is so strong, affecting the growth rate of organisms, in theory, you can reach this theoretical threshold of species persistence, which is an individual threshold. This means that in terms of body size, the body size is so small at the same age that you don't have more fecundity, you don't have more fitness, you don't have more eggs. Yeah, why? Because there is also this other important model linking body size, in this case. Before, body size was in the y-axis, now in the x-axis, and the amount of fecundity, amount of gonadic mass per gram unit, and then you can see that if you increase in the same species, you increase the body size, the amount of eggs is exponential produced. And this was shown in some hundred of species. Okay.
Okay.
Some hundred of species. Can I go?
Okay.
Some hundred of species, and then I suggest you to read the science paper by Barnesh et al. 2018, which is really important. Another model that we just studied that last time is just this type of model. This is a classical type. This is a classical response of all organisms when you put on the x-axis one condition like the temperature. And then we left just in the first part this model, the Sokolova et al. 2012 model. Now we try to understand with just two deep details about some mechanisms, and then later we can try to understand which are possible implications at management level, and then just a really short, a quick example with aquaculture. If this is the model, already Professor Dong, but you know, Professor Dong showed before, you know that this model is really easy, really useful, really understandable, because it is based actually on the Gaussian, on the normal curve. And then the normal curve is an easy model because you have only two parameters, an average, a mean, and a standard deviation. This is a classical response of the temperature response of temperate organisms, and then thermotolerant organisms. If you want to simulate, or if you want to study or to get the thermal tolerance of cold organisms, high latitude organisms, you have just the skewness, different skewness, and then you have this model will be a bit different, but actually is not important, the shape, because we can use this model to predict which is the thermal response of every organism, and this is called the thermal performance curve. We have another types of performance curves when you put more or less conditions on the x-axis. This is from Harley and al. 2017, and then these are classical models that you can use just to predict which is the individual response to the stressors, to climate change drivers, because you have here light, you are here food availability, nitrogen, for example, you have temperature, and also you have some responses that those affect response by toxins. Really quickly, I will show you this type of models. Because in terms of performance, the performance depends on where you are in the biogeographical area of your distribution. And then if you are in the middle of the fundamental niche and then in the middle of the biogeographical area, you are, the species is in theory, is just in the under optimal conditions. And then we can have just, if we measure the performance will be just at the top. If you just increase, these are temperate organisms, and then are just your organisms or just our organism in Europe. If you increase just of a bit the temperature, you have a strong decrease of performance. If you add another, according to the Hans Otto Portner and Sokolova models, if you add another stressor, you don't have a change of shape, you have a change of magnitude, intensity of the curve, and then the curve just is lower. And then if you have more than one stressor, you have the optimum just on the top of the curve, but the performance is just lower. If you have another stressor, you have this strong situation, because just under these conditions, just a few of increment, a small increment, can create a strong decline in terms of performance. And this is when you are just, and this is just the typical conditions of the life on the edge. Most our intertidal organisms just behave, just have this type of response. And this is really important to study, because if you add different stressor, you can have a different kind of reduction. Performance means body size, and body size means reduction in fecundity. And then if you have a reduction of performance, you have repercussions in terms of body size, and then how large is the organisms, and the amount of eggs released per unit of time during the life age of eggs. When you are instead in the margin, at the edge of the biogeographical area, for example, one organism is just here, just is colder, for example, the situation changes totally. And this can produce what we call idiosyncratic scenario, because if you increase, in this case, the temperature, you have an increase of the performance, and in theory is different respect to what happened here, okay? And then is important from where you start. If you put just another stressor, the situation is that, and then if you increase the temperature, is the situation. And this produces different kinds of responses, and then you need to have to pay attention to read just your responses to understand what actually is happening, because it depends from where you take your organism. This is called population effect, and then this is really important. And then behind this type of responses, we have a lot of different adaptation situation. This is the DEB model, and then some of you knows just it. And then when I talk about which are the two main drivers, are just the food just in the top left part, mx, and then the different kind of parameters. This model is useful because you can try to simulate with these typical conditions, because this model is fully mechanistic. This means that if you move just one parameter, we say tweak a parameter, actually you have a chain of different changes at energy budget level. And then if you have a starved organism, immediately you have a repercussions in terms of growth, somatic maintenance, maturity maintenance, reproduction, and maturation. I don't have time to explain you which is the techniques of the technological aspect of the DEB model, but is really interesting. As you can see, if you have different effects at the top level, immediately you have a cascade of different effects. And this is what Professor Donk showed last time. In this case, I linked the habitat to the biodiversity level. This is a really long jump because in the top part, in the left part, you have the habitat. Okay, and this part of the habitat is what Professor Donk explained to you, showed you, is higher temperature, water temperature, rock substrate. The color of the rock, brownish or blackish, is just humidity. Wind direction is wave splashing. In the Mediterranean, we have the wave splashing because we have this tidal, small tidal amplitude. For you, wave splashing when you have 7 meters of tidal amplitude is not important, wave splashing, because you have just a movement of more water masses, and then organisms in the upper part of the shore usually stay for 3, 4, 5 hours immersed under the sun. Instead, in the Mediterranean, with 40 centimeters of tidal amplitude, this is not true, because if you to have the condition of immersion, fully exposure to the sun of our organisms, you must have calm water, calm sea. If you have just a small wave splashing, immediately you have a change of humidity due to the waves. Okay, is totally different the model, totally different the response, totally different the effect in terms of body temperature and in terms of available food. And then the habitat condition that we easily can express in terms of temperature and food availability has immediate repercussions, implications for our functional traits, and for the energy budget of the energy amount that is processed in our budget. And we are there. we put the DEB model there, and then we can measure is what we actually do with our models. We simulate the conditions, the environmental conditions on the heat budget, and then the effects in terms of heat budget, and through the DEB model we can have the two main drivers of the growth: body size and fecundity, growth and fecundity. And then body size is what actually we can say what we obtain in terms of body size is what the organism exposes in terms of interaction with other organisms of the same species and other species. A large body size inside one species means most fecundity, measure fecundity, higher fecundity, but means also measure ability or higher ability to compete with others, compete for the space, compete for the food, compete for the time. And this is really intriguing, because body size is just what we have just to get more food, to swim quicker, to escape quicker, to get more crevices to put our eggs. Body size is the main and the most important performance trait that we need to just understand. Body size and fecundity just are feed the population characteristics, because when we have just a larger body size, we can, as I said before, we can contrast more with other intraspecific organisms of my species. I can contrast more with other organisms from other species. But through fecundity, I have just there is a link with population level, because fecundity and eggs are usually just subjected to the dispersal. The dispersal is really important population function, because is our marine organisms disperse and put the eggs in the water, and the water move the eggs far from the site of production. This is really important. In this case, numbers and quantities are essential. Why are essential? Because if I produce my eggs in the water, and if I give to the water my eggs, this means that I have a really stochastic effects. The stochasticity of this process is absolutely high, because you know that when you produce 1 million of eggs, you can have the recruitment only of 0.01% of that million of eggs. If you produce 1,000 eggs, is different respect to 1 million, to 10 million, to 1 trillion of eggs. This depends from body size, and body size depends from the energy budget and the temperature and food availability, and this depends from the habitat. And then there is a really mechanistic link between or among these different kinds of component of our ecosystem, of our habitat, of our community. The dispersal is the larval mortality. The mortality is really high, and then 99.9999% is more or less 0.00001 of survival. And then we have the recruitment, and when when we have the recruitment, the pressure of recruitment on the community is really important. It depends on numbers of recruiters. If you have more recruiters, you have a certain type of different kind of interactions that these recruiters can have with other organisms of other species. And then interactions, competition, production, grazing, and so on, biotic interactions depend on actually on the quantities of interacting organisms. And this is really, really important. There, we have in ecology a lot of different kind of theories showing which is just the amount of interaction, but this is just not the class, just to show you it. But what is important, the take-home message from this diagram is that if you have an habitat condition change due to climate change drivers, you have a potential repercussions in terms of biodiversity, in terms of interactions. The main issue is that we are not able to simulate this long chain of events that, starting from changes of temperature and food availability, bring us to the density of population, real density of population, and the interaction among species. And then we need, and you young people, young scientists, you need to increase your ability to just simulate this chain of event. This is a cascade. It is a mechanistic cascade, because if you move the temperature in the habitat for the lifespan, for the right time, you have different kinds of repercussions and implications that at the end arrive and reach the final part of the ecological hierarchy, the community level. You have a question? This is a classical curve of population growth. Is just a sigmoid. Easy game for you, because I really know. I really hope that you have some skills about population dynamics. And then if you just think to the possible effects, one effect is just on number and on different kind of parts of this curve. This curve is a density, is based on density dependent processes. And density means numbers of interactors. If you increase, if you increase the number of organisms, of just individuals interacting at intraspecific level, you have implications in terms of food availability, implications of different kind of characteristics of the habitat for the space, and then you have an increasing competition level, and these usually bring the population to have a decrease in terms of carrying capacity. However, I would like to show you that actually all possible, this is a chain of components mechanistically linked, in which the stochasticity of climate change drivers push on that, because you have mechanistic components and stochastic components that are put all together, and then our ability is to disentangle the effect of just to read mechanistically what actually should happen or will happen, and be sure that you have the stochastic factors, or to read also the stochastic factors, and then you just this to increase our ability to predict what will happen in future. But we have the theory showing that if you modify temperature, you have a population implication. And later we have the causal, or just the stochastic effect, other stochastic effects. This is one among the most I like this slide, because this is from Henquist et al. 2015. I suggest to you also in the past with your guys and girls from the Wayne Dog group. In the past, I just showed you this model. This is really important because this shows that if you have different species, then we are able to predict the community structure, and this is how we can try to understand which is the community implications of main modifications at habitat level. In this case, you can see that you have, for example, 3 or 4 species. We have 4 species. Each species in the habitat, in that habitat, has different thermal performance, has different power or light performance, has different performance related to different drivers of change. And then in one habitat you will have some species at their optimum in the middle of the biogeographical variation range. There will be other species that are not the main species. They are not dominant. In an habitat you have dominant species and subdominant species, and this depends on the performance responses at the changing conditions of the habitat. If you move along the x-axis, one species that before were dominant, and dominant means if you remember the population and that scheme that I showed before, performance, this means that you have density, less the dominant species means more dense organism, more organisms of that population. If you move, one species that was before dominant become subdominant, and then you can understand that you have a repercussion at community level just before the food availability and the temperature in the habitat changes, and then through this chain is possible in theory to predict also the dominant and the subdominance of every species in a certain habitat. But we have some issues. In a common habitat, in the common community, we have 200, 300 species. And in theory, we should know the thermal performance of 200 species. If you have 200 species, the thermal performance in theory is just a challenge, commitment for you in the next 20, 30 or 40 years of your life. If you have just ideally, you can have the thermal performance, just only thermal performance of every species from every community. You, in theory, you can simulate under standard, under the certain condition, you can simulate you can predict which is dominant and subdominant. Is huge, a huge challenging task, but in theory we have the theory, but we have the theory to do it. Okay, if you modify the habitat, if climate change modifies the habitat with the Okay, with the different changing drivers, temperature, ocean acidification, etc., we have different kind of actual responses in the habitat. The first effect after later I showed you this structure, the mechanism how I think the community, population, individual work. Actually, we have the first and immediate effect is at habitat level. What we call usually habitat loss. Habitat loss is just a modification of the previous characteristics of the habitat, and then this is called habitat loss. We can have defragmentation of the habitat. We can lose a portion of the habitat if we modify the amount of square meters of the habitat. This means that we lose different species, but we lose space. We lose just food availability, and then these have repercussions in terms of different kind of species inhabiting and living there. Climate change drivers at the community level means through the individual means also an increasing of disease. For example, we can have a different kind of effect, direct and indirect, as I showed before. These are different case studies from different parts of the world showing that climate change usually has affect the different components from directly the individual or just the host pathogen or host dynamics affecting different kind of dynamics. Dynamics. Okay, I'll go to the okay, we don't have okay, we can adjust in these different types of case studies. Professor Donk showed you that if you increase or you modify the thermal patterns, you have a different kind of distribution of organisms. This, for example, the most studied distribution effect is the poleward effect, and then we know that we have, for example, the movement towards north of some species, or just the movement of the deeper layers of the water masses. This is a change of a thermal profile of water masses with immediate effect on the distribution of organisms. The main issue for our main organisms and that our organisms are sessile and then fixed on the substrate like mussels, limpets, and so on. Limpets are just semi-vagile, just a small movement, and they are not like fishes, turtles, sharks, or mammals. One tuna can move. One fish can move. One tuna actually can move if local conditions are not nice, are not good. What is really important is to study the velocity of change conditions. The velocity is called the climate velocity. Some species shift east-west due to coastlines and barriers, for example. However, the velocity of change of the distribution, geographical distribution of our organism is really, really important. And I suggest to you to try to understand which is actually the rate of the change of, and then the velocity of change of distributional patterns of organisms. organisms. We have different kind of effects at the individual, population, and community level. For example, by ocean acidification, the behavior is under ocean acidification condition is a main target of effect. For example, we have a different kind of alteration in terms of sensory perception, olfaction, vision, hearing. We have a different kind of relationship between altered relationship at behavioral behavioral level between different intraspecific organisms and heterospecific, different kind of species. I leave this PowerPoint and then there are a case study. I want to go, because we don't have time, okay, I want to go to the last part. No worries. Okay, and then what I just want to show you is how this type of mechanisms can inform the management of human production at sea. Fisheries and aquaculture was a topic of this class. And this is important because just we need to, how we want to have, we have the wish to predict the performance of organisms is just a wish, also an important wish, a commitment, an important task to predict in terms of management aquaculture and fisheries around the world. And then the main question is it possible to predict which will be the effect of climate change on fisheries or just on aquaculture production around the world in the next 50 years? This is a good question. This is a really important question. For aquaculture, we use, for example, the DBE model. For fisheries, it's not so easy because fisheries is a really complex situation. You have many species, most of these species you don't know nothing about these species. In aquaculture, it is easy because you have sea bream, sea bass, salmon, mussels, oysters. And this is the most production in the world. About the 90% of the world marine aquaculture is just based on 5, 6, 10 species, not more than that. And then we need to try to understand which are the effect of climate change and how we can predict it. And then I just prepared this slide for you, just showing which is the complex situation at the local level when you have a simple cage. No, non è vero. That's not true. Okay, a simple cage. In this case, you have an interaction of the different drivers acting on the growth rate of our organism, which is the main target of aquaculture, that species, cultivated species, grow more, grow quicker than grow really quick just to go to the market before. Okay, but this is the real situation. When you put an aquaculture cage, a farming cage, just in front of the Ginao or just in front of Sicily, you have an interaction of the dozens of drivers, because you have an effect of climate change through just the increase in temperature. We have the increasing frequency of runoff. We can have an effect of ocean acidification, and these are the global level. This global level just is put together with the regional level. For example, at a regional level, we can have eutrophication, we can have microplastics, we can have invasive species. Or if we go at the local scale, we have, and there is an interaction of these factors with the local scale. At the local scale, we can have the hypoxia and toxic contaminant affecting the growth rate of farms, of our cages. And at the micro scale, a sub-local scale, what we call microclimate scale, we can have other 5, 6, 7, 8, 10. The imagination is actually is not so, but we have organic enrichment, we can have pathogens effect, we can have virulence promotion. This is a really huge amount of factors interacting, and the main driver is the climate. And the main driver is the action, is factors human caused, because the eutrophication is due to the waste load to the sea. And then just I simulated for you what is possible to measure at sea actually. And then this is a chain of events happening just in a cage, around the cage, after the first event, which is an extreme event, for example. And then hypothesize, image, and figure out that you have just an extreme event or a heat wave at sea for 5, 6 days, okay? You have this cage, you know that most time fishes usually, or mussel, fishes usually stay in the surface part of the water masses contained in the cage. If there are mussel, long lines of mussels and so on, but however, we have a heat wave. And then we have the first effect is a local increasing of temperature and water column stratification. If you increase the temperature and surface, the density of the water changes, and then you have an effect in terms of stratification. This usually, we have evidence, this usually brings the hypoxia, the oxygen level decline, which means hypoxia. Hypoxia is already the second factor in combination with the increasing temperature and with the heat wave, which is an effect in terms of local organism and population level. The reduction of the clearance rate, reduction of the clearance rate of the filter feeder suspensivores, filter feeder fouling communities. You know that most cages, the hard substrates, are colonized by fouling, which is the main function of these fouling organisms? Filter feeder, right? If you modify the temperature, the clearance rate, the filtration rate of the filter feeders incrusting the hard substrate in the cages usually lower, usually diminishes, usually reduce. Okay, because it is a function, is a performance. This creates the reduction of the amount of availability of fouling organisms. But you know that fouling organisms also has an important effect in aquaculture, the cleaning effect. They filter water and particles, they clean the water, and fishes usually take advantage by these cleaning waters. If there is a reduction in filtration by the fouling, we have a reduction in cleaning rate, and this increase the turbidity, right? The number of particles per liter increases because there is no organism removing them. And this These create an alteration at bacterial community, an alteration in the functions of a bacterial community, and then microbial decomposition rate is altered. This creates another condition, which is the increasing of amount of fecal microbial taxa. And all these possible chains due to mechanisms and mechanistic links caused by the climate change drivers, the extreme event heat wave, actually will have a negative effects on fish growing rate and welfare. But you know, in the Mediterranean, and we just go to the conclusion, when you have an extreme event, a heat wave, for 5-6 days, immediately later, I don't know yet, but I suspect is the same. Later, wow. Can I? Okay. Perfect. Okay. In the Mediterranean, when after you have an increase of temperature by the heat wave, what happens is immediately an increased frequency of runoff. There is immediately a rainfall and then the rain. Okay? The rain is another stressor because since these rainfall events are really strong, the amount of fresh water coming from the clouds is so strong that at local level creates a desalinization, a reduction in salinity. And then you have a chain of events created by the extreme events, an effect on fouling community, an amount of turbidity, a reduction in oxygen level, a chain bringing to the negative effects. Later, you have the rainfall, the desalinization, a reduction in salinity, and the chain, and this negative effect is larger than is possible to predict. This is to show you that when we talk about effects of climate change on marine production, resource production, living resource production at sea, fisheries and aquaculture, we need to try to understand which are mechanisms and which are components of our systems that are affected by different kind of drivers. Unfortunately, I can go more because I could show some application with the DB model next year, next time, and then thank you so much because it was really important, this course for me, this class for me, because I just put different kinds of ideas on biodiversity, on climate, on the mechanistic model, all together just to produce one class, biodiversity and or just climate, science, ecology, climate change ecology. And I would like to thank Professor Donk giving me the opportunity to reflect, to think on this structure. And then, guys and girls, thank you so much for your attention. Yes, no worries.
Oh, I really appreciate learn a lot. The first question, the multiple stressor. For example, you should just show the temperature and low oxygen condition. I'm just curious about the thermal performance curve. If their shape will change or just up and down.
No, the shape is not changed. The theory says that the shape is species specific. Every species has a certain shape. The ideal shape is what is just in the nature, in the reality we measure in the reality. If you increase the number of sample size, then you have a small, accurate, and precise shape. But if you modify the conditions, if you add another stressor, usually you have the change in magnitude, in intensity, and then the shape, in theory, should not change.
Oh, cool. Because
the core of the discussion is that every species has their own shape and their own way to change in intensity, and this is the important from the community level.
Yes. I have another question. For example, if we want some multiple stress experiment,
yeah,
I mean the design, how many groups and to
our experimental design is based on three start from the beginning. We usually repeat the 3 times, and then we have 3 sessions.
So it's 9.
3 sessions. We have 9 individual per level and per treatment. We have more or less 5 replicates of tanks, and then you have 9, 5, 3 per treatment. If you have temperature, if you have contamination or pH, for example, if you have salinity, you have 1, 2, 3. You have this by this, this by this, and this by this. 3, 3, 6. You have the interaction of all 7 scenarios. In every scenarios, you have different kind of 3 sessions. Okay, and then temperature, 3 session, temporal session in different kinds of periods. We don't have season because we don't want to complicate the life, but we have 3 different sessions. With every session has different cages or tanks, or and you have 9 independent samples.
Yes, because they need more simple number. But I don't think we can use this to create it. Just you experiment design, just show the theory, but no prediction yet.
No.
Yeah.
No. But if you have a strong data set based on really conceived, well-conceived experimental design, actually you can try to increase your ability to predict what will happen. Also because, sorry, the temperature, we are forgetting just one important thing. When I think about temperature, you have a different level of temperature.
Different.
Yes, we have 6, 8, 9.
So it's 3 level temperature.
Oh no. We usually have 144 tanks running all together with different patterns of temperature, and we simulate we start from the biogeographical distribution. We individuate the smaller temperature in the biogeographical distribution, the higher temperature, and we simulate every 2 or 3 degrees, they're all pattern. And every temperature, you have 3 sessions, 5 tanks, and 9, and then are 1,000 and 1,000 of organisms. And in this case, you can build the Gaussian or just the response. If you have this, the thermal range and different salinity or different oxygen and so on, you can have a good ability to predict.
Can means 3D model, 2D model.
Yeah.
And another question, the population dynamic of just
There is yes, I don't have the ability to I just brought some papers, carried out some experiment with other people, with Christopher Arley, for example, but we are not able in my lab to run population models linked to the DB. But for me, will be just the objective, the main objective. If you can simulate in the DBE model the effects in terms of fecundity and body size, but fecundity, you can link to the individual population models, will be really nice.
Yes.
Really nice.
Because I think framework is very powerful and very complex. But I don't notice that you have considered the interspecific interaction. The pre and predictor.
Yeah.
Do you consider this?
Yes.
Okay.
Yes.
But we also need some data to validation.
Yes, in this case you can validate. We have different kind of sites in the around the Mediterranean where you can measure the body size and the amount of eggs under different conditions. Ocean acidification, increasing temperature, ocean acidification without increasing temperature. Then there is necessary to increase scale and stationarity of your model. Is necessary. Guys and girls, it's 10 o'clock. Thank you so much. Tomorrow I'll leave. Tomorrow I will leave. And then see ya next November. Okay? Okay, thank you. Oh. If you want. Okay, bye-bye. Thank you so much. Thank you. See you.